Today I have another inverter review for you. Today we're going to be reviewing the Accurate Tools 1500 watt pure sine wave inverter. And this one is notable because it is a 1500 watt pure sine wave inverter that costs around $150 as of this filming. And that's pretty notable because $150 for a brand new 1500 watt pure sine wave inverter is a pretty darn good deal, assuming this is any good. So let's take a look at it and see if this inverter is any good. This is the inverter in question today, and you may notice that it is not in perfect condition. It's not in perfect condition because I bought this used and broken, and I repaired it back to operable condition, and we'll get into that later, but this is the particular sample that I have today. So ignore the cosmetic blemishes to it, but let's go over what this inverter really is. On the end panel, you can see that it is pretty standard. It has an output meter, 4 digits, that you can select between either output watts or input DC voltage, on-off power switch, and 2 outlets, undoubtedly connected up in parallel. The case itself looks to be a traditional clamshell anodized aluminum case, top and bottom half. And over here we have the input terminals. You can see that I did not get a knob for both positives and both negatives, but you'll see soon that that doesn't really matter. There is a single reasonably large diameter cooling fan in it, which is good, and you can see that the components, diodes, transistors and such, are just bolted to the bottom half of this clamshell and not the top. That means that I can safely remove the top to view the insides. Now overall this is a pretty typical construction, but let's take it apart before I even power it up here to see what's inside this particular supposedly pure sine wave inverter. Like most inverters of this type, you can simply remove the top half of the case by removing a few screws. In this case there's just 2 connecting each end panel to the top on each side of the case, 2 on this side. I already removed 1 and 2 on this side. Again, I already removed 1 of the 2. Now, with the screws removed, let's see what's actually inside this pure sine wave inverter from Accurate Tools. And this is what's inside. I'm going to take the camera off its mount now to show you closer up what we're looking at here. This is the inside of the Accurate Tools 1500 watt pure sine wave inverter. And I did have to repair this inverter, so let's get that out of the way first. I had to take it completely out of the case, take off all of the heat sinks, all of these screws on both sides, etc. to repair it. There were a few problems. This inductor over here, which is the output filter inductor for the pure sine wave, this had come loose and broken off, so I had to resolder that on, as well as 2 of these transistors over here were bad, and I had to replace them. After that it worked just fine. I tested it, stress tested it, etc., and it does work perfectly fine once again. But let's take a close look at this. Over here, one of the problems that existed when I got it, these screws were loose on both the positive and the negative side. So it wouldn't have been able to get good power to the circuit boards. This could have been a manufacturing defect or just from use, but either way the design of this does lend itself to vibration issues and such on these screws. There's no lock washers or anything, so they'll come loose over time, and just not a very good design that way. This fan overall is a pretty good design. It blows out instead of in. I don't like that at all, but the thermal design is very, very poor on this inverter. Over here we have the diodes. That's what we're looking at over here. All of these diodes are bolted directly to the outside anodized aluminum case, which is great. And then the fan draws air over the inside of the case and it cools it. But over here we have the transistors for the boost stage. There are 2 transformers over here and 2 banks of transistors for each one of those transformers. These transistors dissipate a lot of power, and they dissipate it directly into this heatsink. However, this heatsink, while bolted directly to the transistors, has no thermal interface to the actual outside case. And there's no direct airflow path over these heat sinks. So there's really no way for them to cool. It's a very bad design, but they do it that way because it fools the user into thinking that it cools well. This outside case doesn't get all that warm. This inside heatsink gets very, very, very warm. And this isn't too uncommon to prevent the outside case from getting hot, but it's a very poor design, and I just don't like seeing that. Over here we have the output stage. Once again, 4 transistors. That's pretty typical, but again they have them bolted to this inner heatsink and not the outer. I really don't like that. Now they did put some effort into putting some of this caulking material onto various components so they don't rattle loose inside, but they used it very sparingly, and this inductor is not caulked down, nor is this one. I took the liberty of zip tying this one down as well as soldering it better than it was originally, so that helps somewhat, but overall the design of this just is very poor, very, very poor in general. Here we have the output outlets, which seem to be decent quality. However, notice that the ground lug, which happens to be this terminal right here, is not connected to anything. The ground lug does nothing. Normally, ground is connected to the outside case for safety. In this case, it's not connected to anything. Now, that doesn't really affect the performance of this inverter, but it's notable that they chose to save the money and just not connect it at all. I don't like that. Over here we can look at the input fusing. There are 2 40 amp fuses for each of these transformers. 2 40 amps over here, 2 40 amps over here. And that is just fine. That's 160 amps total. This is a 1500 watt inverter, so that's perfectly adequate. But there's just 2 transformers and these 2 banks of FETs for each one, which seems a little bit iffy given the size of these transformers. Now, I did take a look at the transistors while they were out, and they are very good quality transistors. These, I forget the part numbers at this point, but they're good quality transistors on the output stage. They are not the IRF 260Ms that are typical of these inverters, which are 200 volt, 40 milliohm transistors. These are actually 250 volt, 30 milliohm transistors, and they're better quality than most, but still it's a little bit skimpy for this particular design. They have a couple different control boards here, which are reasonably well made. I'm not going to complain about those, but the overall construction is extremely poor. Now this is used, and the circuit boards are very, very dirty in here, but ignoring that part of it, they're just not well constructed. The assembly quality is poor. I mean, just little things. For example, let's take the input stage. Here's the input. You have your 2 lugs. You're supposed to populate both, but inside there's a giant bus bar in between both. And given that this inverter is a 1500 watt inverter, you really don't need more than 100 amps or so coming in. This bus bar can handle that. And then it shares it between these 2 wires. One of them goes down here and down into the circuit board, which is fine. This other one comes over here, comes around and up, loops up around, and then comes down here. So why is this wire so long? There is no reason for it to be that long. It's a waste, and they shouldn't have designed it that way. This is extra resistance. These 2 are not balanced, and it won't operate as well. Things like that. Over here we have the 4 input capacitors. Over here they're 25 volts, which I applaud them for. They are a no-name brand, but look at this. They're not soldered down flush to the circuit board, and that's critically important to lowering their inductance. Lower the inductance, the lower the impedance, and the better that they work. They didn't bother to solder them properly. And if you look at a lot of the other components on here, you can also see that they're hand assembled and assembled very poorly. This is typical of a very inexpensive Chinese inverter. Accurate Tools claims to be an American company. It's very clear that American companies had nothing to do with this. It was contracted out and simply built by somebody overseas and rebadged. I haven't seen an inverter exactly like this before, but this is poor quality. Now, that's not to say it's a bad deal. After all, this is really inexpensive. So perhaps this performs okay. So let's see what this actually does in terms of performance next. But before I reassemble this, I want to note that the output wattage meter over here does not work properly. And it may seem like it's just misadjusted, but no, it does not work properly. And there's a reason for that. If you look at the circuit board over here that drives this, here's the circuit board for it. You have an IC with the labels scratched off, which is always a bad sign. But anyway, with the labels scratched off and this little adjustable potentiometer. This potentiometer adjusts the load percent that is shown on the meter on the other side. So this is supposed to show the amount of output wattage, however it doesn't work. I adjusted this as best I could, however I could not adjust it in properly so that it showed the right number at no load, low load, and full load. And that's because it reads the output wattage based off of these two resistors down here. If I can get them in the light, these two right here. And you may notice that there are no resistors present. There are just wires. Yes, wires. That's because they were too cheap to load the resistors. They just loaded a jumper wire and tried to adjust out the variance with this potentiometer. Well, these wires do not behave as resistors. They have a temperature coefficient that is much, much different, and they simply don't work very well. So yes, they saved a few cents and give you a meter that does not work and cannot work, no matter how it's adjusted. Little things like that are a very bad sign of the quality of this inverter. Let's take a look at another thing before I close it up. This jack says fan. Well, you may notice there's nothing plugged in. This fan over here, these two wires run over here and are just soldered directly into the negative over here and into the power switch down there. That means as soon as I turn the power switch on, this fan runs full bore all the time, no matter what. Now, possibly this fan jack has some sort of fan control. I don't really know, but that's not how it was connected up, and this fan just runs full bore all the time. Now, that's not exactly ideal, but it is cheaper because you save a little bit of control circuitry and some transistors, and yeah, that's what they decided to do on this one. So this fan will run constantly, burn power, make noise, and just be annoying. Another thing that's not good about it is that there is not enough ventilation. This fan is adequate, but the ventilation, these are the only holes that exist. This over here, and this over here. Almost nothing. So you hardly get any airflow at all through this inverter. That fan is wasting most of its power, just pushing against a pressure gradient, and there's very little airflow through this inverter because it's poorly designed that way. That's another negative to it. One of the positives is that it does have these large diodes. One here and one here. These are reverse polarity protection diodes. Now, I didn't test this, but the idea is that if you connect reverse polarity to your input terminals, that these diodes should conduct and withstand the reverse polarity current long enough to blow these input fuses. And I somewhat suspect these aren't adequate to actually do that and survive, but that's the idea. And they did spend the money to put them in. Not everybody does. Personally, I don't care, because if you hook these up backward, well, you are likely to damage something, and I don't really care about that, because just don't hook it up backward. Just don't do that, and you'll be fine. Anyway, I'm going to reassemble this now, and let's actually see how well this thing performs. Its construction quality is subpar, but its price point is also subpar, so we'll see how those things trade off. Here's my test setup. I have my Accurate Tools 1500 watt pure sine wave inverter connected up through these two 2-gauge battery cables, which is perfectly adequate for a 1500 watt inverter. Have it connected up through this 250 amp fuse to two deep cycle batteries. These are fully charged and in good condition. And also I have it connected up to a 45 amp charger, which will keep these batteries certainly topped off, plus provide about 45 to 50 amps of additional boost to them. So here's the inverter. For the load, I will run that through a kilowatt P3 meter, which I will just simply plug into this outlet. These outlets, by the way, are reasonably good quality, so no complaints there. I'll turn this on and turn off the loads, because apparently I left those on. And here's the inverter. It is outputting 125 volts, and the display here says 14:00. Well, that's actually 14.0 volts. I'm not sure why it's a colon, but we'll ignore that. And the load is 110 watts, even though there's 0 watts. I did my best to adjust this meter based on that adjustable potentiometer, but this is about as good as I could get it. It reads about 100 watts too high at no load, and about 100 watts too low at full load. And that's about the best that I could do on that. You may notice that the fan is running and it makes a fair amount of noise and blows very little air. Now this fan actually isn't a bad fan, it's just that there's nowhere for the air to come into this box. It's completely sealed except for a few little holes here and a few little holes here. And it's just not enough. They really should have put better ventilation in this and it would have performed much better for almost no additional cost. Again, very poor design. And I venture to say that this wasn't really designed at all. And they just put it together, but that's pretty typical of these cheap inverters. Anyway, let's see how well it performs. And I did test this out before, so this isn't the very first time that I powered this unit up. The output voltage right now is 125 watts, but if I start loading it down, I have an electric heater plugged in, as well as some 100 watt light bulbs, as I often do over here. And if I just take my electric heater and turn this on to the fan setting, I'm not sure if you can see that on camera. Let me turn on the light bulb. That may help. There we are. With 100 watts of light bulbs going, the voltage dropped a little. And if I turn my heater on low, you can see that the voltage drops significantly. I'll now turn it on medium, and the voltage dropped to 100 volts. If we look at the wattage, it's only drawing 700 watts, and already the voltage dropped to 100 volts. The input voltage, if we take a look at that, is 12.8 volts, so the input voltage is very much adequate. But this is one thing that I noticed about this inverter: its output voltage is not very well regulated. Let's see what happens when I turn this heater on high now. Notice that if I turn the heater on high, the output voltage actually increases. And the wattage went up to 1200 watts approximately. And that is because this particular inverter seems to have various taps. I turned it back down to medium on my heater again. Now instead of 100 volts, I'm at 115. This inverter seems to have various different taps where it gets stuck on, where it will boost the voltage up to a certain voltage, and you're guaranteed between about 100 and 130 volts, but it could be anywhere in between there depending on which tap it happens to stick on. I may not be describing that very well, but the voltage regulation isn't very good with this particular inverter. It basically allows the voltage to droop down to around 100 volts, then it switches to a different internal boost setting and bumps that voltage back up. As the input voltage sags or the output current increases, that sags down again, and when it hits the bottom, it boosts back up again. And either time when it hits the top or the bottom rail, it readjusts to the next tap, if that makes sense. So the voltage isn't very well regulated on it. However, it does seem to keep it between around 100-ish and 130 volts, which is adequate for most appliances. Now that does mean that things like electric lights are going to flicker when loads change, but it depends on what you want this inverter for. If you're powering certain sensitive loads, that may not be acceptable. If you're powering power tools or things like that, maybe you don't really care. So let's test out this inverter a little bit more and see what kind of loads it can actually power. Let's first see what this inverter can handle for a continuous wattage draw. Right now I have 5 100 watt light bulbs running, and it's drawing about 430 watts at 110 volts. Let's see what happens when I turn my electric heater on high, which should be about 1500 watts additional. And it does output around 1400 watts at 100 volts. So it sags significantly, but it does output 1000 to, here's 1300 watts right now. Let's screw in a couple more light bulbs, see what happens. Oh. And My room is now full of smoke. Not sure if you can see that, but this inverter just smoked. So, good thing I had my quick disconnect on the battery, but that is not good. So, let's take this thing apart and see what blew up. Here's the inverter with the top off, and I am rather unhappy to see that this particular transistor here blew up. And this is not one that I had touched. I didn't touch the input stage whatsoever on here, but that particular transistor decided to give up when I loaded it fully. And it didn't do that when I was stress testing it earlier, so I'm not exactly sure what that means, but I guess I'm going to have to repair this inverter once again. That's unfortunate.